Let's get started again. So once again, we have Dr. Jennings, who's going to talk about weighted quantile sum regression and recent extensions. So thank you, Dr. Jennings.
My pleasure. I am so delighted to be here. Dr. Svensson's introduction this morning made me think about the importance of taking sort of applications that we do, sort of in academics, all the way down to the place where it really matters, and that's at the places like the CDC. So I'm really excited about being here and talking today. So weighted quantile sum regression and recent extensions. So I just realized when Marianthi was talking, this is not an updated bubble plot, but this is one of the original, very famous Marianthi bubble plots, describing the importance of research questions. And I will absolutely concur with that it really depends on what your question is. And if you have a different question, you might not anticipate having the same result as if you're trying to address another question. But the focus of WQS regression is really, or my interest is really this idea of what's in the bubble is called the overall effect estimation, but I think of it more specifically as, is there a mixture effect? And when I say mixture effect, I actually mean that in a very, very specific way. And this comes from the toxicology literature. Back in, what was the date? 2002, Andreas Kortenkamp's group published this very interesting paper. I think it was 15 chemicals together. And they described this phenomenon of something called something from nothing. And the idea is that this was a toxicology study, right? The idea was given exposures, it may have been an in vitro assay. I should look it up and tell you guys, but I don't actually remember. I think it was an in vitro study. They had concentrations of these 15 chemicals, one at a time, was very much below an effect level. But when they put the chemicals together, those 15 chemicals at where each one by itself was not even close to having an effect, the joint action of those chemicals together had a significant effect. And that's the idea of the something from nothing. So individual exposures may be very low, but the fact that they may be working jointly in some way, they may be on the same adverse outcome pathway or things like that, then together you would have a significant effect. So of course the concern is if you don't think about the possibility of this joint action, then you could underestimate risk. And that's something we don't want to do for sure. So my research questions end up being, if you have C components that are in this mixture, and when I say mixture, I don't necessarily think of that the mixture is the exposure at the same point in time. I think with biomonitoring data, we are measuring, the evidence of exposures to a lot of chemicals from many different sources. And I would maybe consider that unintentional mixtures, but they're based on our individual exposures, from diet, they could be very specific to individuals, but unintentional in the sense that they weren't created together to produce a product, right? Those are the things that we're exposed to. The point is, though, to try to measure this thing, something from nothing, maybe we could use an index. That's the idea of weighted quantile sum. Can we use a weighted index to identify components that might be acting jointly? Now, that doesn't mean that every individual has the same set of components that are acting in their bodies, but it gives you sort of a overall level of components that may be combining jointly to have an adverse effect. And so the idea is with this weighted index, we sort of have two different parts of that. One is we would be able to identify the components through this weighted index. It's a single degree of freedom test, which means it's going to be more powerful. And also then once we estimate the weights, and we can interpret them, then we can characterize the components that might be the most impactful. So again, I guess this is what I just said. The idea is focusing the inference. So if your hypothesis is that you're trying to find the set of chemicals that lead to or may be associated with an adverse effect, then you know the direction of that adverse effect, right? So to focus the inference in that direction ends up being a more powerful test. we put the chemicals in, or the components in, it doesn't have to be chemicals. So let's say they're chemicals, components of the mixture in terms of quantiles. And we do that so we can interpret the weights. If you have a weighted index and the components are all in quantiles, then you can interpret the weights. You know, the higher the weights, that would be higher the association for that chemical or sets of chemicals. The quantiles then put everything on the same scale, and that's the important part. The other thing is, once you get the weighted index, so there's going to be two parts of the weighted quantile sum regression, but once you get the weighted index, you don't have to worry about multicollinearity and the reversal paradox. And the other thing about WQS regression is this idea of an ensemble step, where we're going to select weights and things across random sets of either people or subsets of components. And so I'll talk about that in a little schematic here. So a little, okay, suppose we have, so this is just a little cartoon, but suppose we have here 4 different phthalates. That's meant to be that, you're supposed to be looking at I don't know how to point to this. Let's see. Like a heat map of correlation. So the color codes there is meant to say these are things that may have a very complex correlation pattern, and that's typical for environmental exposures, right? So we would have an example where we have components that are correlated with a complex pattern. We're going to put these things in quantiles. So what does that mean? That means that we're going to score the concentrations across subjects in terms of quantiles. It could be deciles, it could be tertiles, it could be quartiles, whatever you'd like. And of course, then we can always do sensitivity analyses to evaluate, did that matter, the quantile that we chose. But what that means is for every individual, whatever their concentration is, here I just demonstrated with MEHP, you would, across the subjects, then you would quartile them, or decile here, I guess, and then I'm going to rank score them. So here it'd be 0 to 9 based on the observed concentrations. Now, of course, we don't have to have everything in the same, you know, in equal sets. Mainly what we're trying to do is to get things in the same range. So if you want to make zeros be really zeros, you can do that, and then have the quartiling be above that. So there are features of that that you can play with. So we take our subjects, this is the animation part. My colleague did this, I think it's really cool. And we split them into 2 parts, the 40% and the 60%. Why am I choosing 40 and 60? I'm going to train on the 40%. We get the estimates of the weights on the 40%. I'm going to hold out a little bit more on the 60% because that's what I'm going to test on. That's going to be the beta coefficient, and I'm going to estimate the association, there. And so I might want a little bit more power. So that's maybe why we would hold out the 60%. You could do 50-50. You can play with this a little bit. So we take the training data, see this animation cool, and so we estimate the weights, right? This is a nonlinear model. I'm going to show you that in the next slide. But we're going to estimate the weights for that set of components. This is actually going to be a bootstrap sample. I'll talk about that in just a minute. I'm going to randomly select the training set with replacement, and then I'm going to estimate the weights, and suppose they're given here for these four components. And then the advantage of a bootstrap sampling is then I can go back and do that again as many times as I want to. So what you see is then this is the effect of the bootstrap sampling. You're starting to see the variability in the weights just by randomly selecting different bootstrap sample. And so we can do this, say, 100 times. And then we take an average. Okay, so the one-step part, the first step of a weighted quantile sum regression is to estimate those weights across multiple bootstrap samples. And again, that's to start to see the variability in the weights as you change the bootstrap sample. And what do I mean by that? Marianthi was talking about, the complex correlation patterns and things, but let me just use my fingers as a correlation set, right? Suppose you have 3 chemicals in your set that are highly correlated. In a single analysis, you might only have a weight on one of those, right? And it might be because that's just the representation of that correlation pattern with that single component. But if you change the bootstrap sample, maybe the next time it becomes the weight goes to one of the others, or it goes to the third one, right? So by looking at this over different bootstrap samples, then you start to see the signal might kind of go across that correlation pattern in a way that you could pick up with that ensemble step. So anyway, we get the average of the 100 bootstrap samples, and we create our index, and we're going to estimate that on the holdout data set. So these are all quantile scored, but at the end we just have a weighted index, and then we take that and put it in. We could put that in the training set, but we would anticipate that if we put it in the validation set, the holdout set, it's going to be a little attenuated because the validation data were not used in the estimation of the weights, right? So they're not going to be, it's not going to be as strong of an association there. But the beta coefficient we're interested in is the one from the holdout set. So we might get a beta coefficient and p-value. Now, this is not the end of the story, but this is the beginning of the sort of the root part of weighted quantile sum regression. So here it is. This is little Caroline Carrico. She was a PhD student back in the day. That this was her dissertation work. So here you see this in the equation form. The interesting thing I want you to think about here is in this first equation. So this is a generalized linear model. So we could do this on logistic model. It could be an added, it could be a identity link. It could be a logit, whatever we want there. So it's not just continuous values, but we can estimate these parameters. So we've got an intercept, a slope parameter associated with this weighted sum, and then these are the covariates adjusted in the back, right? But the point is, this first step is actually a nonlinear model, and that's because we have a beta 1 multiplied by the weights. So in this first step, this training data analysis, right, we're going to have to use a nonlinear estimation algorithm to estimate those parameters. The advantage, well, the disadvantage of that is it's not a closed form solution. We've got to do iterative algorithms to get those estimates, but there's all kinds of algorithms that can be used here. But the interesting thing about a nonlinear modeling estimation step is we can actually constrain the betas, right? We can constrain parameters in a certain way. Why would we want to do that? Again, back to my idea of the adverse outcome in the direction of that. We might want to say, I want to do this analysis in the direction where beta is constrained in the direction of my hypothesis, right? So Brent Poole's word on that is I'm encoding that into my analysis, right? I'm choosing this direction because that's what I anticipate. I'm studying these chemicals because we think they're adverse, and so my direction of my hypothesis is in that direction, right? So that's the idea there. So we could actually constrain the beta 1 to be in the direction of our hypothesis and estimate the weights accordingly, right? Now, there may be a case where some of the chemicals are adverse and some aren't. And in that case, we want to be able to sort of say, well, if we're looking at chemicals in one direction, the weights that go with that direction would be different weights if we look in the other direction. So we want to make sure that we're not averaging across things that don't make sense, right? So, and that's part of the way the algorithm that we're working on works. But okay, so we do the bootstrap sampling, we come back and we get the average weight, the W bar there's the average weight across the bootstrap sampling. There's a little bit more of a technicality here. Here's the weights across the B bootstrap samples, but we're actually going to have a weighted index where the weight, we have something we call a signal function. So we might choose to weight the bootstrap samples that have a little bit stronger signal, maybe on a T statistic of that beta, something like that, to sort of emphasize those as being the ones that are a little bit more informative towards our what we're looking at. But anyway, so you can choose, that's a part that you can choose in the GWQSR package, what that signal should be. I won't say more about that today, but okay, so here's the validation data. So once we get the WQS, the weighted index, we've defined the weights that we're going to use across our bootstrap samples, then we get a weighted index. Now it's just, in the next step, it's just a variable we're putting in the regression model. So in this bottom part here, this is now just a generalized linear model, right? The WQS is a variable that we've defined, and we can put it in our model with the covariates and estimate the beta one there. So that would be the p-value if we stopped here, but we're not going to stop there. So we've got another step. So here's Galabello and Paul Curtin were colleagues that this part of this was Golub's dissertation work as well. We don't have to do the bootstrap samples, right? The idea of the ensemble step is to try to get more variability in to allow for that variability that's based on the correlation pattern to be part of our analysis. So we can do that with the bootstrap sampling. We can also do that instead of with the bootstrap sampling, we could say, let's randomly select, instead of subjects, we're going to randomly select subsets of the components. So now suppose I've got 1,000 components, right? And 1,000 might be bigger than my sample size. Oh no, right? So the 1,000 components, if I randomly select those many, many times, I can still get a weighted index, right? So that's what Golub's dissertation was, where he said, well, let's take C components. Maybe we'll take as a criterion, let's just say the square root of C is the number of subsets, the size of the subset that we would choose. And we do that many times, say 1,000 times. You may need to do more than 1,000. But it's the same idea of randomly selecting. Now we're going to say we've got 1,000 components, randomly select, say 22 or something, do an estimation, do an analysis, and then go back and randomly select again. Now, in this case, all the subjects are together, but the neat thing about the random subset part of this is you get the capability of sort of decorrelating that correlation pattern, right? You choose 22, you might bust up some of those correlation problems, right? So, and you do that over and over again. And as long as you're kind of confirmed that you've had every component have the opportunity to be in at least one analysis or whatever your criterion is for that, then you can say, I've done enough of the many random subsets. So I shouldn't say just 1,000. It really could be more than that. But then you average across all those random subsets and you get a weighted index. So it's the same kind of thing in terms of an ensemble step. It's just not bootstrap sampling. Now it's across the components. The very interesting thing, and this addresses Marianthi's point in her last little case study about the seed, we actually now are interested in a repeated holdout data set. So now instead of, remember how we split the validation and the training into that 40-60? Now we say, let's go back and do that again and do this whole process again. And let's suppose we do that 100 times. So that's what I mean by the repeated holdout. We're going to do that whole process that I just talked about many times to start to see the variability in the estimation of the betas and the weights. Oh, so here we go. So this is Eva Tanner. This was her, it's a MethodX paper, came out in 2019. But the idea is, so over on the left-hand side here, is it your left? Yeah. If these are our subjects, we split them into training and test, right? And to get the weighted estimates and to test the beta in the holdout set, right? But what Eva said is, well, let's do that many times. And so you can see the different colors of the faces there to identify that you get a different set every time you pull that 40-60 or 50-50 split, right? You get a different set. Every time you do that, you get a different set of weights, you get a different beta. So, and Marianthi showed that in one of her slides. We're going to see that distribution as we go forward, but that's what we would anticipate. This is actually really interesting information, right? You're seeing the variability in the weights and the variability in the betas, and that's given the very complex correlation pattern that we might have. So just a word about an analysis strategy. I think it's sometimes interesting to look at analyses with covariates and without covariates, just to sort of see the impact of the covariates. So, and like I say, you could get an early idea what, you know, it's better to walk before you run with these analyses. You need to have a sense of your data. So sometimes you say, well, let's do a weighted quantile sum analysis without covariates, and we're not going to constrain the betas initially. And let's just see, out of those sort of 100 bootstraps or whatever, let's suppose we're doing the bootstrap part. Suppose we do that. How many of those betas are negative? How many of those betas are positive? You can actually look at that in the analysis to see what's the sort of signal in the data there. What's the data telling me before I start saying, let's just look in a certain direction? You can kind of study that. And then you could do this again by adding covariates. Well, did it change much with the covariates? Again, maybe look at it first, just initially, before, without constraining, right? And then if there is a signal in the analysis, in the data, then you could constrain in that direction. Now, it might be that this could be a confirmatory step to say, I'm correct in the sense that these are chemicals I would anticipate to go in a certain direction. And that's my hypothesis. But this is still preliminary steps that give you some sense of what the data are saying. There are really only, I think, 4 scenarios. One is the beta one is positive, that there really is a positive association, or beta one is negative. There really is a negative association. We could have data in both directions, right? So then we need to think about that as well, or maybe there's no association at all. So those are the things that we need to think about. What I'm going to show you, though, is an extension of this also, where we allow for stratified interaction models. And instead of sort of going through the formulation of that and things, I think it might be easier just to see it through an example. But the idea is we do a lot of work with endocrine disrupting chemicals, right? We would anticipate endocrine disrupting chemicals, the EDCs, may have differences between boys and girls, right? So we want to be able to maybe have a strategy where we could estimate weights for boys separate from the weights for the girls. So we would allow for different weights across boys and girls, and we could have different betas for that. So let me just sort of demonstrate that with an example. So this is the Selma cohort. It's a Swedish cohort. Carl Gustav Bornehag is the director of the study. These are 26 chemicals. And you see them listed. I don't know if you can really read that, but you see them listed there. These were, there were 2,300 women that were evaluated, but based on covariates and things, that this sample size is down to 700 based on the outcome that we were looking at, 7-year IQ. But what you see here is the list of the chemicals. And the interesting thing also about this study is this was first trimester. A lot of these pregnancy cohorts are later than first trimester, but this is first trimester. The median sampling time was at 10 weeks of gestation. But what you see here is the chemicals listed and maybe the metabolite or whatever from the biomonitoring, the limit of detection, but also in that highlighted column, what you're seeing is the percentage of subjects where these things were detected. And many of these are at 100%. So again, that's evidence of human exposure is to multiple chemicals, not one at a time. But we know that walking in. But this is a kind of interesting confirmation of that. And the next part here, and I'm not going to go into this, but I think this is really important, and maybe at the CDC and other places, regulatory people might want to think about this as well. The green and the red dots there have to do with what's available now in terms of biomonitoring equivalent levels, indicating whether or not these exposures are at a high enough level to be of concern. All but the 2 PFASs there are green, indicating that according to biomonitoring equivalent levels, that would be regulatory values based on that have been translated back into the urine or the serum based on, you know, what the particular analyte is, would indicate there's no concern. One at a time, there's no concern. But we're seeing so many of these, you know, epi studies where we're seeing associations that don't really agree with that. So I think this is, again, the importance of human exposures and mixtures, that we really need to go more than just one at a time. Okay, so here's a little example of the stratified interaction. So the idea, again, is to have different weights for boys and girls in this example, and also different beta coefficients. So what you're seeing here, we're looking at prenatal EDCs, 7-year IQ in the stratified interaction weights. And what you're seeing there are if you can kind of see this, their distribution of weights across those 100 repeated holdouts, right? So you're seeing that variability in the estimation depending on where you split the data to begin with. And that's really interesting information. I think it goes towards generalizability of the results, right? Because every time you split the data differently, the training set has a little bit different characteristics in terms of the covariates and all of that. But what you see here this is a divergent plot, and the blue are the boys and the red are the girls. And what you're seeing, this is on average. So the solid diamond on the left-hand side are sort of summarized over here, but side by side, you can see there is sort of a difference in terms of the average weight between boys and girls. And that's what we might anticipate. We're looking at endocrine disrupting chemicals, right? So we might anticipate that there would be differences. What's on the bottom though is every time we do a different split, we get a different beta. So we get a distribution of betas. So we can look at the confidence interval on those betas from these different splits, right? So what you're seeing at the bottom here are the standardized betas separate for boys and girls. The blue is the boys and the red is the girls. And if you can see where the 0 mark is there, the boys have a significant decrease in IQ that's associated with exposures prenatally, right? And so, and the weights, the average weights are given here for the boys. The girls, although there was a negative estimate, it's not a significant estimate, right? The distribution of betas there, I should say it's a negative estimate on average, but with the confidence interval, it's not a significant association in the girls. A little bit of an aside, but this is my new sort of interest. The green here is nutrition. I created something called the My Nutrition Index. And the My Nutrition Index is a personalized index based on an individual's characteristics that might be based on your body size, your activity level, your sex, your age, all of that, but also medical conditions. Do you have IBD? Are you in an IBD flare event? Do you have, all kinds of behavior-based and medical-based sort of differences across people? What's right for you in terms of your nutritional evaluation depends on you. And that's the whole idea of the My Nutrition Index. So we evaluated the My Nutrition Index in this sample. So these are prenatal nutrition values from a food frequency questionnaire that was then translated to nutrients. And what you're seeing here, which is the point, is that the My Nutrition Index is positively related to IQ, right? And what does that mean? That better nutrition prenatally is important, but we know that walking in, right? But what we don't know is what's a reasonable metric to evaluate that. And so we're using the My Nutrition Index now to sort of evaluate that in some regression models and that. But we're also now starting a My Nutrition Index app. And this is new days, but we're early stages with that, but I'd be more than delighted to talk to anybody who's interested in talking more about using a nutrition app, because I think if we can evaluate the My Nutrition Index as a metric that is meaningful, then maybe people can make decisions about how to eat to improve their own situation based on such a metric. So this is all, wide open research questions, but maybe we're at the beginning of something that could be fun to evaluate. But here the point is that nutrition stands against it. We have these adverse exposures that maybe these moms had no idea about or had no way of dealing or changing their environmental exposures, but they sure can decide how they're going to eat, right? And so there's the positive side of that. Okay, now my advertisement is off. So here's another study. Well, I've got another advertisement thing here. This is actually part of the HERE repository. So if you don't know about HERE, HERE is the Human Health Exposure Assessment Resource. It's an NIH funded thing that has gone for a handful of years. And the idea is that investigators could apply to HERE, the HERE network, and given the review process and all that, if they were accepted, then they could send their study samples to the HERE labs, have them be evaluated, with the epi data for their study comes into the repository, the data repository, and after an embargo period, those data are publicly available. So if you go to the HERE, HEAR, Human Health Exposure Assessment Resource data center, you can get access to this repository. Now you have to register to be part of that, but that's not an onerous process. And then you have access to these publicly available data. Of course, they're all de-identified and all of that, but then it's a lot of very interesting studies, different designs, different research questions, different health outcomes, et cetera. So I really would encourage you to go look at that. But this is a study that was part of the HERE consortium early on. It's from Uganda. These are children with malaria. And they were actually hospitalized. These are pretty severe illnesses. So the children had malaria. They were either cerebral malaria or severe malaria anemia. And I'm not a doctor. I don't know really the difference of that, but there are two different kinds of malaria that they were evaluated. So these are kids in the hospital. The outcome here is a composite scale of 12 months after they were released from the hospital, a measure of neurodevelopment, right? We had 17 micronutrients and metals and a bunch of covariates there having to do with maybe the weight that was Z-scored might be a surrogate for nutrition. The Z-score for height might be a surrogate for stunting. So, there's a lot of variables here. This is a kind of a complex study. So we ran this analysis with the GWQSR package. And to give you a sense of this, now, this is just single chemical, one at a time, although it's all in one table, a single chemical evaluation adjusted for these covariates. And I've highlighted the ones with p-values, say less than 0.1. But what you see is there are some of these components that are positively related one at a time. And some, the one that jumps up that's negative is vanadium there at the bottom. But we know that this is complex data because some of these chemicals might also be in food sources. So you might think it's a bad chemical, but it could be really being it's a confounding issue with rice or things that could be a nutritional thing. So it's complicated to analyze these data. So we don't really know if it's we wouldn't say everything is in a positive direction or a negative direction. So but that's what we're looking at in this analysis. So this is a heat map of the correlation pattern, not as complex as what we see sometimes. Okay, so here's the result. Randomized, repeated holdout WQS stratified interaction model. So we see the covariates there. Now remember, we're randomly splitting the data 100 times and doing analyses. So we get 100 different sets of weights, 100 different beta coefficients. And so what you're seeing here are the median estimates of those 100 beta coefficients, and then the 2.5 percentile and the 97.5 percentile estimate for the kind of confidence intervals on the betas. It's a stratified interaction model. So that means we get with a 0-1 on the strata identifier, we get the reference level. So this is the reference, I guess the CM group, the cerebral malaria was the reference group. So this would be the slope estimate for that group. And then down here would be the difference between the two groups, right? And what we see here is there's really not a significant difference in terms of the interaction for these two groups. But we could also, from the beta 1,2 and the beta 1 up here, we can estimate what the second group would be. So the SMA group here. And so that's beta 1 plus beta 1,2. And we can put a confidence interval on that, right? That's borderline significant. They're both kind of borderline significant, really, but 84 out of 100 of the beta 1s were positive. It doesn't meet the 5% there. But for the SMA group, we end up with 97 out of 100 are positive. And, well, that's maybe all I'll say. I would say that's at least borderline significant for the SMA group. So although they're not statistically significant in terms of their slope, we do seem to have a stronger signal in the SMA group than the CM group. And this is the result that we get. Again, the different box plots and weights across the different 100 repeated holdouts. We might focus a little bit more on the SMA group there, but antimony and cadmium and cesium and arsenic are the ones that kind of pick up there. I'll say a little bit more about interpreting these in just a minute. But you do see a slight bit different weights in the two groups, which you can kind of identify with the divergent plot there on the right. Now, looking at those divergent plots, make sure you're realizing that's not positive and negative, it's positive and positive, right? They're like histograms side by side, okay? Okay, so I think the next slide, yes. So this is now, we call this the Buscane criteria. This is Stephanie Buscane was a colleague at the HERE Data Center, and she's the one that really sort of championed this idea of putting the criteria around how to interpret these plots. So what we say is, and it's a good idea to do this always sort of the same way, and that was her point about this. So when she left, I said, okay, we're going to call this the Buscane criteria. So if you publish this, you have to say the Buscane criteria. Anyway, so if 90% of the weights are above, okay. The threshold part here, if you can see this little red dashed line, that's the equi-weighted mark. So if the signal is larger than the equi-weighted mark, then we say, well, that's something we should look at. If the signal is sort of below, that's not something we're so interested in. But now we've got this distribution of data of weights above, around that threshold value. So the Buscane criteria says that if more than 90% of our repeated holdout weights are above that threshold, then we say that's a probable association. That's a pretty strong evidence. 90% or more of our weights are above that, right? We see some cases like the ones that are in the purple box. In the purple box, it's not more than 90%, but still, more than half of the data are above the threshold. And so we would call those maybe possible associations. Now, the additional criteria is, I don't think I would distinguish between the median and the mean. I'm not going to split that way. So I would say if the bar or the mean is above the cutoff, that maybe we would put that in the possible association. We can also, in this case, and I'm not going to emphasize this, but we can look down on the other side and say, zinc and manganese, they're hardly ever above that, more than 90% below. So we could say they're probably not related, at least in the positive direction. And they may be associated in the negative direction, but they're not associated in the positive direction. Okay, so I'm gonna show you the double index. So I'm not quite through. I know when you see the summary slide, you go, yay, we're done. I've got a little bit more to do. But here we've identified a mixture effect. So the weighted index is the thing. These are the components that we think might be acting jointly, right? They may be on some adverse outcome pathway, but certainly we would anticipate that maybe there's a little bit stronger signal by looking at them together than one at a time in terms of this idea of a mixture effect. We did detect stronger associations in one strata compared to the other. So that was the advantage of that stratified interaction. And of course, it doesn't have to be just boys and girls. It can be, SES levels, it can be stress levels, it can be whatever you're studying. That idea of stratified interaction, I think, is really interesting and useful to look at. With the Buscane criteria, we could define differences between probable and possibly associated with the outcome of interest. And again, it's beyond the scope of this workshop to say antimony being positively related to neurodevelopment. What? I mean, but that could be a confounding problem, right? It could be a food source that's related to, and then that nutritional value is important. So those are things that, the scientists around this, the doctors around this should be really aware of those kinds of sort of issues and complexities of these modeling. Okay, so this is Stefano Renzetti. He is also he manages the GWQSR package. If you have questions about the GWQSR package, he's the friendliest guy in the world. He's in Italy, so he's 6 hours away from us in terms of time zones. But if you have questions, certainly he's one person that you could reach out to. His dissertation work, though, is this, that the idea of a double index weighted quantile sum regression. And what that means is that, we've got the same set of components, but we want the data to sort of tell us in which direction the weights should go in. So we're constraining to have a beta that goes positive and a beta that goes negative. The problem is it's the same set of chemicals, right? So these two components, so we get a PWQS and an NWQS, positive, negative. But those are two components that are highly correlated, 0.98, 0.95, whatever, right? Just walking out the door. So we have instead of the usual constraints in our WQS model, now we're adding something called the lasso penalty term. And now this lambda parameter that you see here, we're going to have to set that. So it ends up being a little bit more work to figure out what that lambda parameter be. The lambda parameter is largely trying to downweight things that really aren't associated to pull the correlation of these two weighted indices apart. But setting that lambda is one of the things that you have to do. At the end of the day, though, you get a WQS in the positive direction and one that's associated with the negative direction, and you can test, in both directions. So I'll demonstrate, one more here. So in terms of setting the lambda parameter, one thing that Stefano worked on was the idea of using an Ikaiku criterion when lambda is set equal to 0, and then evaluate the model at various sort of multiples of that. So if we define the AIC naught as the AIC when lambda is equal to 0, maybe consider a model where it's 0.1, a model where it's 10, to kind of give you a range of sort of penalty terms and then choose the one that's the smallest. And we can also look at the correlations. He also talks about using the tolerance, which is related to the inflation factor and things like that, to try to evaluate what's going on. So there's a little bit more complexity there. But then you run this and allow it to run in both directions. I think the next one, yeah. So these are the results of that study from the Ugandan study. And so you see here that there's hardly any difference between the lambda equal to 0 and lambda equal 40. It's actually a smidge smaller, right? When lambda is equal to 0, meaning no weighting on the lambda. And the correlation there is 0.82, which is kind of smaller than a lot of studies. I mean, this is still new days on the double index, right? But a lot of the studies we've looked at, the first step of this, they're correlated above 0.995, something like that, right? So in this case, the 0.82, maybe that's not so bad to start with. But I actually did, but you see though, as the lambda changes, you see how the correlation changes between the two indices, right? And that's the whole point of the lambda, is to try to pull them apart. But I ended up focusing on the lambda equal to 40 for this example in the repeated holdout analysis. And that's what you see here. So when people say, oh, they're going positive and negative, how can it be positive and negative? This is the answer to that question, right? What we're seeing is that the components that are weighted higher in the positive direction really have very little weight in the negative direction. And vice versa, the ones that are really low here are higher here. So that's the point. There can be different patterns in the chemicals, and we're trying to find the signal in both of those directions. What we see here, again, this is with 100 repeated holdouts with lambda equal to 40. We do see a positive beta on, this is the median of those 100, and this is the 2.5% and 97.5 percentile. So you see it's a significant positive association. It's not quite negative. The negative one, although the median is negative, it's not quite significant, but kind of close in the negative direction. And again, like you see, the negative have different weights than in the positive direction. Okay, so we did see then at least an indication in both directions, but the significance was in the positive directions. We can use the Buskine criteria again in both of those that we wanted to. Here I just wrote this up in terms of the positive association since it was the one that was significant. And again, this idea of, you could think about having how do we interpret this, that antimony is helpful? But again, the confounding issues and things like that, I think people need to think about that, which is beyond my expertise to interpret that here. So that's it. I mean, these are the colleagues that have sort of helped build this up, and I appreciate, of course, all of their work. Vishal Midya is going to speak later today, and he's also a colleague and is doing some nice extensions as well. So I didn't include him here because he's going to stand up and tell you his own story. But anyway, I appreciate the time, and thank you very much.
Well, thank you guys for waiting.
Thank you. So we have time for some questions.
Remember how long?
15.
We have 15 more minutes.
15 minutes.
Okay, good.
So if you have some in the room, please go to the microphone. A couple of questions came in. from people following online. And I think you touched on these a little bit, especially at the end there where you talked about the negative association with antimony. But let me just read the question and maybe you can expand a little bit. So the question was, does the WQS assume that all of the exposures are additively adverse, or can it account for exposures that can attenuate as well as be perhaps beneficial at the same time?
Right. Right. So you're right. The double index is a way of addressing that. Yes. I don't know what else to say more than that. I mean, it is true. I think that, you know, if you do an analysis of complex correlated variables and put them all in a regression model, you could have the reversal paradox that just because the things are correlated, some are going to go positive and some are negative. I think with a correlation of above or around 0.4, they actually go opposite. And that we see correlations above 0.4 all the time. So yeah, I think having the weighted index is a way of sort of avoiding that, especially with the ensemble step of avoiding that reversal paradox. But I do agree with the questioner about sometimes there are positive and negative, which was the case in this with this Ugandan study. Yeah.
Thank you. Another question, I think maybe from the same listener was, is it possible to have to do this kind of weighted analysis using non-equal groupings, such as natural breaks? And I understand that part of the purpose of using the quantiles is so that everything is sort of on the same scale. But I think the groupings may have been, you know, if there's a natural break, does that work? But it seems like it gets away from the same scale issue, perhaps.
Yeah, so you're thinking what they're saying about natural grouping is in terms of the potency or whatever of the concentrations. Do you think that's what they mean by natural groupings?
I thought it maybe meant either
that or maybe a break in the distribution.
Yeah. Of the concentration.
Of the concentration.
Yeah.
Yeah.
Yeah. Yeah, I mean, there's no requirement that the groups have to be of the same size. And like I say, some of the work Vishal has been doing and we've been doing with microbiome or metabolomics, sometimes what's zero really is zero and you don't want to mix that up, right? So we have done analyses where you can allow for the zero to be zero and then maybe just for convenience, you know, use tertiles or quartiles or whatever above what's zero to sort of distribute out the concentrations above that. And I think that works fine. That's not now an option. I mean, you have to code that yourself in R to do that, but that's doable. And in our package, you just don't let the package change those weights or those quantile scorings. But I do like that idea of the, you know, below the limit of detection, just make those zero and then pull out the others. Yeah. Because the main thing is multiplying the weight times the range. It's not so much the distribution of how many are in each group.
Thank you. We have a question. Could you introduce yourself? State your name.
Yes, I'm Georgia. I'm from Chemical Insights Research Institute. So I have a, thank you for the presentation, by the way. It's very nice. So I have a follow-up question about the grouping. So have you ever tried to apply this WQS model to a classification scenario, especially for the categorical classifiers, and especially for more than 2 classifiers? Because most of the examples seeing right now is for the regression. I'm just wondering if we can apply the same techniques to the classification scenario.
Say more what you mean when you say classifying. Do you mean, go ahead.
So yes, so for the so this will be more a case for the categorical data.
Okay.
Instead of those continuous variables. So I wonder if there's a adaptable way we can apply these techniques to those categorical variables.
Yes.
And more than two variables.
Yes. So yeah, it's a very interesting question. And I have done a little bit of work in that regard. So the way I'm understanding what you're saying is instead of having mixtures of components with a continuous concentration, you've got categorical variables you're trying to go for, like questionnaire data and things like that. Is that what you're asking? Yeah. So one of my colleagues at Mount Sinai, Megan Horton, is working with the World Trade Center data set. And there were questionnaires about the responders there and their time on the pile and all kinds of questions. But the questions, I don't remember if it was 3-level questions or just 2-level questions, but there were hundreds of questions that were part of this questionnaire. And she did WQS where the questionnaire values were let's say there were just 2 levels, like low or high or no or yes or whatever, right? And she did a WQS on that and had some really interesting results with different kinds of variable sets and things, domains and things. So yeah, it's possible. And it might be a very natural way of using WQS because you're already on those scales and you're just trying to say which one of these questions are the ones or the sets of these questions that are most related to some. In her case, I think it was some PTSD thing that she was evaluating. So it was a really interesting study, but yeah, I mean, if you have that kind of application, I think it would be a very interesting way of going. Yes, sir.
Thanks for your talk. I'm curious about the application of results from WQS studies to processes like risk assessment and using data from studies for decision-making in public health. Do you think WQS is well suited to that process because it provides a summary measure or index compared to other mixtures methods? And could you just comment on that in general?
So, so you're thinking about risk assessments with exposures that?
Sure. Yeah.
Yeah. So yes, I think we've actually done WQS analysis as part of a process where we were looking at a whole mixture approach. And the way we did that was this, and there may be other ways of thinking about it, but this is the way that we've published. This was working with the EDC Mixed Risk Consortium. It was a Horizon 2020 study that we published in a science paper a couple years back. But the idea was to say, let's take prenatal exposures. It was the Selma cohort that I showed you, and identify the components that are most related to, I think it was 2-year language delay, right? Which is a precursor to IQ. They're highly correlated. And we found these are the components that are most associated with that from a WQS analysis. And then we took those chemicals, looked back at the pregnancies and said, what is a typical exposure of those chemicals in those moms, right? So that's not the weights from WQS, but we used the WQS to identify the components. And then we said, now let's find a typical exposure, geometric mean of these components. Now there's a lot of waving of the hands there, which would be better now with the HTTK software that's come out by the EPA. But back in the day, we did our best. And we actually constructed that mixture, and that mixture was evaluated in brain organoid assays in Xenopus what am I forgetting? Zebrafish, and in a mouse study, et cetera, many different studies across Europe to look for points of departure in these different assays. Right. So we've got a human relevant mixture that was reconstructed in terms of typical measures. We did assays, multiple different assays relating to neurodevelopment. And then we took a point of departure from those dose response curves and then said, okay, now let's use this concept of sufficient similarity, right? Now we've got an index that we say is a reference mix. Sorry, we've got a mixture that is a reference mixture. And now we can go back to the Selma or to other, we also compared it to NHANES exposures to, and so we said, now that if you are sufficiently similar to that reference mixture, then let's evaluate you in terms of what we call a similar mixture risk indicator, which ends up saying, how high is your exposures relative to that point of departure? Right. So let's suppose, so we actually then now more recently have published that reference mixture in NHANES. We said women of reproductive age, how many of you are sufficiently similar? So this is a Selma cohort where we had the mixture constructed from. in the US with the sampling weights, it was like 60% of those women, if I remember correctly, of the women in the US are sufficiently similar to that mixture. Okay, of those 60%, how many of them have high exposures relative to the point of departure from that thyroid dysfunction measure on this Xenopus assay? And it ended up being, 1 or 2%, but that represented 1.1 million women in the US. Right. So we're not using just WQS to do this, but all of those sort of parts together, I think is kind of a nice complementary, supplementary way of thinking about risk assessment. Is it's human relevant mixture, and then, but it's got that sort of causal part really in the assay. So we, what we said might be related to neurodevelopment, we actually had evidence in these different assays about thyroid dysfunction, or about, various things, the brain organoids, all of these kind of interesting things. So I don't know if that answers your question, but that was a really fun study to do. And I hope that we can kind of advance some of those steps, identify other mixture studies that we can use for such points of departures, and this concept of sufficient similarity, and et cetera.
I have a question. So thank you so much for your great presentation. The question I have is, and it could be very basic, how do you do this analysis in SAS? Because I'm a SAS user, so I don't understand packages that well.
So you're talking to me because I'm also a SAS user from way back in the day, but we decided to do the publicly available coding in R. But here's my message to you. Don't give up on R. It took me years to struggle to say, but we've got examples now. You can do all your data manipulation in SAS and put it in a CSV file. And then with some really nice coded examples, you can pull it into R and very directly get the GWQS package to work for you. So I think even SAS users, you don't give up on that. I think the GWQS R package, it's harder to do data manipulation in R if you're a SAS programmer. I understand that, but I think with some nice vignettes and coded examples, you can do it.
Looks like, I think we have time for perhaps one more question. In the context of overall, is there a mixture effect question? Can you give us a sense of when you find the method most useful in terms of numbers of components of the mixture, for example, and sample size a little bit? I haven't talked much about sample size, study size, but really I think it's about the number of components in the mixture.
Yeah.
At both high end and low end.
In terms of sample size, or high and low end components?
Components.
Yeah, I like to kind of push the bubble a little bit, or the envelope, whatever the phrase is. Humans are exposed to all kinds of chemicals. Way back in the day, Moise Montez is in the room. Way back in the day, we were kind of forced to say, let's just look at these pyrethroids, and we're not going to worry about the other pesticides. We're not going to worry about, these chemical classes, which are not, those subsets are not based on human exposure. So I'd much rather say, we've got measures on all these different chemical classes. Let's put them all in the model and do a WQS regression, right? I would rather do that than do a subset analysis of, well, here's the phthalates and here's the parabens and here's the, right? Because what does it mean at the end, right? I like them all together. Now, are there limitations of that? That's where I start doing sensitivity analyses, right? That's where I might start saying, well, what if I hadn't put them all in? What if I had put a subset in? Do I get about the same thing, or things like that? I do like the fact that we can do WQS in cases where the number of features is larger than the sample size. I think that's a nice exploratory place. Marianthi doesn't like exploratory, and I kind of agree with that, but I think, you kind of get a sense of what's happening, but with more sensitivity analyses to say, so, how sensitive is that result to various kinds of alternatives to that? But I'd much rather try to represent real human exposure to more components than less components, because that's more what's typical in life. But realize, though, that when you put weights on all these chemicals, that doesn't mean everybody it's not a mixture. Everybody has their own mixture. My WQS index is going to be based on the weights that were estimated across subjects, but that it's based on what my higher concentrations are, right? So my WQS index is going to be different than yours based on our exposures, right? If my phthalates are low and yours are high, the weights on the phthalates are going to, be more important to you than to me, that sort of thing, right?
What about at the lower end with just 4 or 5 components? Do you find it useful in that context?
I do. But let me tell you the other thing that we do for preliminary look is, a lot of epidemiologists will take the concentrations of their exposures and log transform them and report regression analyses on that, right? I also would like to see in a preliminary look, the single chemicals on the log transform, because that's what people want to look at, but also on the quantile scale, right? The quantile scale is sort of the building blocks to what we do in WQS. The WQS is just a weighted values of those quantiles, right? But the comparison of the log transform versus the quantiles is telling you something about the extreme, maybe telling you something about the extreme values in those distributions, right? If even in a log transform case, you could still have influential observations. You put that in a decile or a quartile, it can only be so influential, right? It's pulled down. So if you get different sort of results between the quantile, single chemical quantiles and log transform, I think that's informative. Now I forget your question, but I'm just telling you my experience with doing that.
It was about if you only had in the components, there are maybe only 4 or 5.
Yeah, but even 4 or 5, I think you can see how they, more than just one at a time, right? I think you can see sort of the concept of a mixture effect there.
Great. Well, thank you, Dr. Jennings.
It's been my pleasure. Thank you all very much.